In this next set of videos, we're going to look at mutual inductance and a couple of applications of mutual inductance in what is known as linear transformers and ideal transformers. So we'll start out with a review of inductance. We'll then introduce this concept of mutual inductance and then look at both linear transformers and ideal transformers. As you know, an electric charge has an electric field associated with it. One of the remarkable things about electric charges is that when that electric charge starts to move, there's also a magnetic field that is induced by that moving charge. The direction of the magnetic field can be found by placing your thumb in the direction that the charge is moving, the thumb of your right hand in the direction that the charge is moving, and then the fingers of your right hand will be pointing in the direction that the magnetic field is oriented. The magnetic field wraps around itself, and magnetic fields, as you know, don't have a point source. They are, you can think of them as being bands, much like a rubber band. It's important to keep in mind that that magnetic field exists only while the electron or the charged particle is moving. If the charged particle stops moving, there is no magnetic field associated with it. Now, the magnetic field can be intensified by taking the wire and looping it around itself in a coiling process and laying those coils next to each other. So each one of these wires in this coil have current flowing through them, and each one of those current carrying conductors has a magnetic field associated with it. And so by coiling them and laying the coils next to each other, you actually intensify or magnify or concentrate even this magnetic field. The net effect is that you create a magnetic field that flows along the length of this coil. Sometimes these coils are called inductors, and the more coils you have, the more flux or the greater the strength of the magnetic field. So the magnetic field, and we sometimes refer to the magnetic field as its flux. Flux then is proportional to the number of turns in the coil times the strength of the current flowing in the coil times something that's known as its permeance, or rho. Permeance. Another amazing physical property associated with these is that when the flux changes by changing the current, a voltage is created across the terminals of the wire with a polarity that opposes the change of the current. Now let's think about that. Here we have a coil, and it's got current flowing. If the current is constant, the magnetic field will be constant. But if the current changes, the magnetic field changes, and a voltage is induced across the terminals of the coil. Now this voltage that is induced, the polarity of this induced voltage, is such that it will oppose changes in the current. In other words, the induced voltage attempts to prevent or oppose changes of the current. Let's do the math here. So V then is equal to N times the change in flux with respect to time. So that's equal to N times, now as you look at the flux term, N, the number of turns is a constant. The permeance of the material of the core is a constant. The only thing that can change is the current, and so we get N times rho times di dt. These terms right here are constants and are parameters of the physical construction of the coil, and we lump those all together in what is known as the inductance of this coil. And we get then that V is equal to L times di dt. That expression we're familiar with. It tells us that the voltage that's developed across the coils of a coil with a changing current has a proportionality constant. I'm not saying, let's say it a different way. The voltage that is induced across the coils here is proportional to the change in current with respect to time. And that proportionality constant, which is a constant and dependent upon the physical construction of the coil, is known as its inductance. Thus, this inductance quantity L is proportional to N squared. For each turn of the coil, you get a squaring effect on the magnetic field or on the inductance of that coil.